Hello everyone, welcome to my video. In this video, I'm going to introduce the definition of deformation gradient tensor and also show you how does the deformation gradient looks like for some simple deformations like simple shear, elongation, rigid body motion, and also bending. Okay, let's get started. In order to talk about deformation gradient tensor, first we need to consider we have a material to say like this in a reference configuration that is undeformed, B, and we consider a material point with location vector x, uppercase x. So after a deformation, it becomes like maybe this shape, and then we call it the configuration BT, and the material point uppercase x becomes lower case x vector, and we can just construct a coordinate system here like this. So this would be E1, E2, E3. Okay, let's say we have a orthonormal basis in a Cartesian coordinate system, and so that these vectors are basically the x vector, and this is the uppercase x vector, and then we have this vector is the displacement u equal to lowercase x minus uppercase x. That's it. Okay, so now we have a material point deforms from uppercase x to lowercase x at time t, from the reference configuration as undeformed configuration B to the current configuration as a deformed configuration BT. And now we can define a deformation gradient, a deformation gradient F equal to partial x over partial uppercase x. So this means that F is a second order deformation gradient tensor which equals to the partial derivative of the current configuration position vector x with the partial derivative with respect to the undeformed original uppercase x vector. And the component form is like this. And that's it. That's the definition. Okay, so in order to further understand this, okay, so first probably I will just write out F would look like, as you can see, consider a three-dimensional case that we have partial x1 over partial x1, and then partial x1 or partial, we change j, partial x2, partial x1 over partial x3, right? Follow this equation. And then we have I equal to 2, so it's this, and then j equal to 1, right? And then we have, we have both of them equal to 2, right? Okay, 2, 3, and the last line can be similar. Down. Okay, so now let's consider a very simple case that first let's consider a simple shear deformation. Let's consider a 2D case that, for example, we have a coordinate E1 and E2, and we have a material originally like this shape, and then we apply a pure shear, so the material becomes like this, and we define this length as gamma, and here is 1. This line is 1. Okay, in this case, so, and also the black box is like the original configuration, and the blue one is the current configuration. Okay, so first we write out the relation between current configuration H is a function of the original material point vector and t time. So this equal to, consider along E1 direction is H1 plus, because of this because of this shear deformation, so we have this term H2 times gamma. So this is along E1 direction, and then along E2 direction there's nothing changed, so it remains the same like this. Recall that F equal to partial X over partial uppercase X. So it simply becomes consider X like here. It's S1 over uppercase S1. So this one. So it's X1 over uppercase H1. It becomes what? It becomes simply 1, right? And then second term, H1 over uppercase H2, and here it becomes gamma. And then we have H2 or lowercase H2 over, that would be this one, H2 over H1, that's 0. And then H2 over uppercase H2, that's 1. So that's the deformation gradient tensor, 1 gamma 01. Very simple, right? Now let's consider another case. Let's consider an elongation problem. It's very simple, as similar before. We have this. We have a deformation. We have a bar like this before, deformation, and then we stretch it to be longer. It becomes like this. So the deformed, let's say the deformed length is alpha L, and this undeformed length is L. So in this case, we can write the X vector as alpha X1, that's along E1 direction, plus, because E2 there's nothing changed, so the same as before, and that's simply it. In this case, we can similarly, we have Fj equal to Xi over partial uppercase Sj. So in this case, we can simply write as, so X1 over uppercase S1, that's alpha, and then we have X1 over uppercase S2, that's 0. If over H2, we have partial H2 over uppercase H1, that's 0, and then it's 1. So this is simply a elongation. That's simply the deformation gradient for the elongation along one direction. Okay, now we have seen simple shear, elongation, and then let's consider rigid body rotation. If rigid body rotation, it's a little bit complicated. Let's see. Let's consider a case. This is the coordinate. And imagine we have a material here. We have a rigid body here. And first, we rotate it with respect to one material point, like one reference point, maybe they're here. We name them as O. Name this point as O. So we do a rotation, for example, and it becomes here. So let's imagine this is the deformed material. Just rotation. Just rotation with nothing else. Just rotation, that's one thing. And then we do a translation. Then we move it to here. To here. Okay, so if we say this is a function ct, this translation, and also we say this rotation is a function, is a tensor qt. So in this case, we can write the deformation as x at c t plus qt minus o, right? Here you have to understand this is that because this is the origin, this is the origin of the rotation. So this denotes the coordinate with respect to the rotation reference, the O vector, and this is a rotation tensor, and this is just a simply transition. Okay, if we admit this, then we can get the deformation gradient tensor just as before this equation. So we can simply write this. Oh, actually, we do not really need to use that. We can directly apply our tensor form equation, and then we just substitute this whole thing. We will simply get, let's see, this one 0, this one 0, so we simply get qt. So in this case, the deformation gradient tensor is the same as the rotation tensor. And recall that rotation tensor, for example, one example of the rotation tensor in 2D case would be cosine theta minus sine theta, sine theta, cosine theta. This is very common used. For example, we have a coordinate, and then you have we have a material. We have a, for example, we have vector here. If we want to rotate it to here with a angle theta, then we have the rotation tensor. We have the rotation matrix is R like this form. But anyway, here that we don't need to use this, but this is just used to give you an idea of what the rotation tensor, what the rotation matrix looks like in 2D case. And here, recall that we have the relation for the rotation tensor, that is, if Q is a rotation tensor, then we have the transpose of the Q equal to the inverse of the Q. That's one property of the rotation tensor. So if that's the case, that means, for example, Q inverse equal to the identity tensor. So the determinant of it is equal to the determinant of identity tensor equal to 1. And also because determinant q equal to determinant q inverse, and also determinant of two matrix equal to the determinant of the product of the two determinant of the two vectors of the two matrices. So in this case, we get determinant of the q equal to minus or plus 1. Okay, if that's the case, and also here note that a proper rotation corresponds to q equal to positive 1, because the rotation, as you can imagine, that if we rotate the material from here to here, the volume should not change because we did not deform it. We just rotate it. It's a rigid body rotation, so the volume should preserved. And the one physical meaning of the determinant is the volume. For example, that if q can be described by u, v, w, these three vectors, it's the physical meaning of the determinant of q is the volume that's spanned by these three vectors u, v, w, like this. So it would be like this, right? Yes, it would be like the volume of the u, v, w, like this. This is the physical meaning of the determinant of q, and because of this, that the determinant of q must be positive 1 if this is a proper rotation. And if we have the determinant of q equal to minus 1, that is corresponding to a reflection. As you can imagine, that the volume become negative, so it's like a reflection with respect to the coordinate, and that's about it. Okay, so we just talked about what the determinant of q is here. Well, actually, we do not need to know that much, but basically is that for rigid body rotation, the deformation gradient is just the rotation tensor. That's it. Okay, and then let's consider a case with more complicated deformation. That's the fourth case. We call it bending. For this bending problem, I will not focus on too much on the equation here, but just introduce the physics. Let's say that we have a beam that it's a cantilever beam that we deform it. So something like this. So for a material point, we have here to here, so we call this v is a function of x, uppercase x. This is a function v, and also as you see that we have the axis moved from here to here, so we have rotation, and we call the rotation angle is theta. It's also a function of x. Let's see, we do not put x right here, but we put x1 on it because we have e1 here, e2 here. As you can see, it's not a function of e2, but we just define them as a function of e1 at uppercase x1. Okay, and now I will just give you the equation directly. Okay, let's see x oops, time. Okay, so okay, I will not, because okay, I will just write them out as this because it's a little complicated. I don't want to let you get confused. Okay, how about let's consider 3D case here. This will be, although it's really a 2D problem, but I just would like to give you a sense that what the 3D problem would look like is very similar. Okay, in this case, and it's 1 here, it's simply it's 1 minus it's 2 sine theta. Oh, remember this theta is a function of x1 and time. Actually, here we should have time, here we should have time. Okay, and x2 is simply x2 plus the function v, that you remember, function of uppercase x1t minus, due to the rotation, we have this term. This theta is a function of x1t, as you remember. Okay, so that's for x2, and x3 it's simply x3 uppercase. Okay, so in this case, apply our equation for the deformation gradient tensor. Okay, we can simply get, for example, f11 equal to uppercase partial x1 over partial uppercase x1. That becomes, for this term here is 1, so it's 1. Here we have uppercase x1 here, so we have minus x2 sine theta becomes cosine theta, and then we have partial theta or partial x1 because theta is a function of x1. So that's the case. And for f12, partial x1 over partial uppercase x2 equal to minus sine theta, and also f13 partial x1 over partial uppercase x3 equal to 0. Similarly, we have f21, as you can see, this is a function of x1 and this is a function of x1, so we have here is partial v over partial x1 let's see, okay, here is 2, okay, and we have, so here we have minus the positive, but cosine theta is minus sine theta, so it's minus sine theta, and then partial theta partial x1, right, that yeah. Oh, and also we have this x2 here. Okay, so we have this, and right, that's it, yeah. And then we have f22. Let's see what this f22 looks like. F22 is, so first term is 1, then v term is 0, and then minus x2, so it's minus cosine theta because cosine theta is a function of x1. Then it simply becomes 1 minus 1 is 0, and then simply becomes cosine theta. And then f23, as you can see, is also 0, and then f31 is 0, f32 is 0. As you can see that f3, that the x3 is just a function of uppercase h3, so then we have 3 equal to 1. Okay, in summary, that we have this deformation gradient tensor looks like minus h2 cosine theta partial h1, and then minus sine theta 0. Then it's partial v partial h1 minus h2 sine theta partial h1, and then cosine theta and 0, then 0 0 1. Okay, so this is the deformation gradient tensor for this bending problem. Okay, so now in summary, what we have done: first, I introduced the deformation gradient tensor, the tensor form definition, and then this is the component form, and this is what it looks like if we write out the components. And then, given this definition, we consider 4 simple deformation cases. First, it's for simple shear. We consider a shear with a deformation gamma, and here we can see that the deformation gradient tensor is with gamma in this component because there's no elongation. So for the diagonal components, they are all 1, and because we have shear along E1 direction, so we have gamma here, and gamma. So we have gamma here, and if we have elongation along E2 direction, we expect to have gamma in this position. That's what we learned from a simple shear. And for the elongation case, very similar, because we do not have shear, so it's 0 0 in the shear term positions, and because we have elongation along E1, so it's alpha place, it's in the E1 direction, it's in the 1 1 direction, it's in the 1 1 component, sorry. And if we have elongation along E2, so we expect that we have elongation alpha in the E2, that is component 2 2 position, and that's what we learned from the elemental elongation problem. For the rigid body rotation, we considered a transition that is C, and then we consider a rotation that is Q. And as we can see that the deformation gradient is just the rotation tensor, and because we know that that's it, right? And the rest of this, I just showed that the determinant of the rotation tensor should be 1 for a proper rotation case. For bending problem, it's a little bit complicated, but what we learned that eventually we get this is the deformation gradient tensor case. If you have any questions, please leave a comment, and also comment on what you would like to see in the future. If you enjoyed this video, please click the thumb up and like it. Also share with your colleagues. Alright, with all of this, see you next time. Bye.